Lesson 16, Finite Integrals and Area Under Graph. Hello everyone, I'm Dennis. This video is brought to you by Ace with Dennis. Now, learning can be smart, not hard. Don't forget to subscribe and press the bell notification button to stop missing out free lessons from me. In finite integrals, there are a few laws that we need to obey. Here are the laws. Law number 1 is the one that we use to do the finite integrals. If integration of small letter fx dx equals capital letter fx plus c, then integration of small letter fx dx from a to b equals bracket capital Fx a to b. So from here, this is the meaning of finite integrals, where we set a limit for the integration. So this is the lower limit a and this is the upper limit b. So after we integrate, we get the second function, which is the capital Fx, and we limit it from a to b, which means it is equal capital F b minus capital F a. We substitute the value of b equals to x into the function f minus we substitute the value of a into the x in the function of f, and this is how we perform the finite integrals. Later, we will see some examples how we can perform finite integrals properly. Law number 2. Integration of a to a fx dx equals to 0, which means if the lower limit is same as the upper limit, the integration will give us 0. Number 3. Integration of a to b fx dx equals minus integration of b to a fx dx, which means if we swap the value of the lower limit and the upper limit from a to b to from b to a, it will be negative. Next, law number 4, integration of a to b k fx dx. So if there is a constant k multiplied with the function, so what will it be? I guess you should be able to know the answer, as it is very similar with finite integrals, which is we can take out the k out of the integration. So it's k integration of a to b fx dx. Number 5, integration of a to b fx plus minus gx dx equals, I think you also know what will be the answer, because it is also very similar with finite integrals. So if there are two functions, either plus or minus, inside the integration, then we can integrate them separately. So it becomes integration of a to b fx dx plus minus integration of a to b gx dx. Law number 6. Integration of a to c fx dx equals integration of a to b fx dx plus integration of b to c fx dx. This is also similar with the chain rule in differentiation. So if I integrate from a to c, will give me the same result if I split the integration into two parts, which is I integrate from a to b followed by integration of b to c. So this is law number 6, and please remember all these 6 laws of finite integrals before you want to perform any finite integration. Now, let's see how we can perform finite integrals in algebraic functions. Here is an example. Evaluate each of the following integrals. A. Integration from 1 to 3, 3x squared minus 5 plus 2 over x squared dx. B. Integration from 0 to 4, square root of 64 minus 7x dx. Here is the solution. For A, integration from 1 to 3, 3x squared minus 5 plus 2 over x squared dx. Before we want to perform any integration, we should change the fraction into indices form, which gives us integration from 1 to 3, 3x squared minus 5 plus 2x to the power of negative 2 dx. And now we can perform integration. For 3x squared, we get x cubed. For minus 5, we get minus 5x. For 2x to the power of negative 2, we get 2x to the power of negative 1 over negative 1. Then we put the square bracket, limit from 1 to 3. Now we can simplify the expression, which becomes x cubed minus 5x minus 2 over x, limit 1 to 3. Then we substitute x equals 3 into the expression, minus we substitute x equals 1 into the expression, which gives us 3 cubed minus 5 times 3 minus 2 over 3 minus x cubed minus 5 times 1 minus 2 over 1. Then we calculate the values, which gives us 11 and 1/3 minus negative 6, and the answer is 52 over 3. For B, integration from 0 to 4, square root of 64 minus 7x dx. Before we want to perform integration, we should put it into the indices form, which gives us integration from 0 to 4, 64 minus 7x to the power of half dx. Now we can perform integration, which becomes 64 minus 7x to the power of 3 over 2. Remember, we copy the bracket, we get 64 minus 7x, and then the power plus 1, half plus 1, we get 3 over 2. Then divide by the power plus 1, 3 over 2, then followed by differentiation of the bracket, differentiate 64 minus 7x, we get negative 7. We put the answer at the bottom, negative 7. Okay, and the limit from 0 to 4. Then we can simplify, and do you notice that this is a constant where we can take out the constant negative 2 over 21 outside of the integration so that it won't give any influence to the integration, right? So it becomes negative 2 over 21 bracket 64 minus 7x to the power 3 over 2, limit from 0 to 4. Now we substitute x equals to 4 into the expression, which gives us 64 minus 7 times 4 to the power 3 over 2 minus substitute x equals 0, which becomes 64 minus 7 times 0 to the power 3 over 2. And we calculate the values, which gives us minus 2 over 21 times negative 296, and the answer is 592 over 21. Now, you can try this example yourself. Evaluate each of the following integrals. A. Integration from negative 1 to 1, 3 times x cubed minus 2 over x squared dx. B. Integration from 1 to 4, sub x times 2x minus 1 over x dx. C. Integration from 0 to 3, x cubed times 1 over x minus 2 cubed dx. D. Integration from 2 to 6, 2x minus 3 square minus 1 over square root of 2x minus 3 dx. You can pause the video and try to solve it yourself. So here is the solution. Integration from negative 1 to 1, 3 times x cubed over minus 2 over x squared dx. So do you notice that we have a constant 3, and the denominator, there is only one term. So what we can do is we can take out the constant outside the integration so that it won't impact the integration, and then we can break this fraction into two fractions, which is x cubed over x squared minus 2 over x squared. Then we simplify, we get 3 integration from -1 to 1 x minus 2x to the power of -2 dx. And now we can start to perform integration. Integrate x, we get x squared over 2. Integrate minus 2x to the power of -2, we get minus 2x to the power of -1 over -1, limit -1 to 1. Alright, then we substitute the values inside. So, we simplify first, which is 3 times x cubed over 2 plus 2 over x, limit from -1 to 1. Then we substitute the values x equals 1, which gives us half plus 2 over 1 minus substitute x equals to -1, which becomes half plus 2 over -1. Then we calculate the values, which gives us 12. This is the solution for A. For B, integration from 1 to 4, sub x times 2x minus 1 over x dx. So now we change everything into indices form first, which is integration from 1 to 4, x to the power half times 2x minus x to the power of -1 dx. Then we multiply the x half inside the bracket, which gives us integration from 1 to 4 to x to the power of 3 over 2 minus x to the power of -half dx. And now we can start to integrate. Integration of 2x to the power of 3 over 2 gives us 2 times x to the power of 5 over 2, because the power 3 over 2 plus 1, then we get 5 over 2, divided by 5 over 2, minus x to the power of half, because -half plus 1, we get a half over half. So put the square bracket, limit from 1 to 4. Then we simplify, which gives us 4 over 5 x to the power of 5 over 2 minus 2x to the power half, limit from 1 to 4. Then we substitute x goes to 4, which becomes 4 over 5 times 4 to the power 5 over 2 minus 2 times 4 to the power half, minus substitute x goes to 1, which gives us 4 over 5 times 1 to the power 5 over 2 minus 2 times 1 to the power half. Then we calculate the values, which is 108 divided by 5 minus -6 over 5, and we get the answer is 114 over 5. Next, for C, integration from 0 to 3 x cubed times 1 over x minus 2 cubed dx. So, do you notice that these two functions have the same power, which is x cubed? So, we can combine them together, which becomes integration from 0 to 3 bracket x times 1 over x minus 2 cubed dx. Now, we can multiply the x inside the bracket, which gives us integration from 0 to 3, 1 minus 2x cubed dx. And now we can start to perform integration, which gives us 1 minus 2x to the power 4 over 4 times -2, limit from 0 to 3. Simplify, we get -108, 1 minus 2x to the power 4, limit from 0 to 3. Then we substitute x equals to 3 inside, which gives us -108 bracket 1 minus 2 times 3 to the power 4 minus substitute x equals to 0, which becomes 1 minus 2 times 0 to the power 4. Then we calculate the values, which give us -78. Here is the solution for D. Integration from 2 to 6, 2x minus 3 square minus 1 over square root of 2x minus 3 dx. So notice that the denominator has only one term, and it is 2x minus 3, similar with the top 2x minus 3 square. So we can break it into two different fractions, which gives us integration of 2 to 6, 2x minus 3 square over square root of 2x minus 3 minus 1 over square root of 2x minus 3 dx. Then we change it into indices form, which gives us integration of 2 to 6, 2x minus 3 to the power of 3 over 2 minus 2x minus 3 to the power of negative half dx. And now we can perform the integration, which gives us 2x minus 3 to the power of 5 over 2 over 5 over 2 times 2 minus 2x minus 3 to the power of half over half times 2, limit from 2 to 6. Then we simplify, we get 1 over 5 2x minus 3 to the power of 5 over 2 minus 2x minus 3 to the power of half, limit 2 to 6. Then we substitute x equals to 6, which gives us 1 over 5 times 2 times 6 minus 3 to the power of 5 over 2 minus 2 times 6 minus 3 to the power of half, minus substitute x equals to 2 inside the expression, which gives us 1 over 5 times 2 times 2 minus 3 to the power of 5 over 3 5 over 2 minus 2 times 2 minus 3 to the power of half. Then we can start to calculate the values, and we get 228 over 5 minus negative 4 over 5, which is 232 over 5. Now let's see how we can perform the finite integrals in trigonometric functions. Here is an example. Evaluate each of the following integrals. A. Integration from 0 to pi over 4, 6 cosine 2x dx. B. Integration from 0 to pi over 2, 2x minus sine 3x dx. Here is the solution. For A, integration from 0 to pi over 4, 6 cosine 2x dx, we can take out the constant 6, which becomes 6 integration from 0 to pi over 4 cosine 2x dx, so that the constant won't affect your integration. Now we can perform the integration, which gives us 6 times sine 2x over 2, limit from 0 to pi over 4. We simplify it, which gives us 3 times sine 2x, limit from 0 to pi over 4. And now we can substitute x equals pi over 4, which is 3 sine 2 pi over 4, minus substitute x equals to 0, which becomes sine 2 times 0. So we calculate the answer is 3. For B, integration from 0 to pi over 2, 2x minus sine 3x dx. So we can perform the integration. For 2x, we get x squared. For integration of sine 3x, we get negative cosine 3x over 3. Limit from 0 to pi over 2. Simplify, we get x squared plus 1 over 3 cosine 3x from 0 to pi over 2. Then we substitute x equal to pi over 2, which gets us pi over 2 squared plus 1 over 3 cosine 3 pi over 2, minus substitute x equal to 0, which gives us 0 squared plus 1 over 3 cosine 3 times 0. Then we calculate the values, which give us 2.13 as the answer, which is rounded off to 3 significant figures. Okay, now you can try this example yourself. Evaluate each of the following integrals. A. Integration from 0 to pi over 8, 4 cosine squared 2x dx. B. Integration from 5 to 10, 2 sine 3x minus 5 plus 3 cosine 2x plus 3 dx. You can pause the video and try to solve it yourself. Here is the solution. For A, integration from 0 to pi over 8 for cosine squared 2x dx. We can take out the constant, which give us 4 integration from 0 to pi over 8 cosine squared 2x dx, so that it won't influence your integration. And now, remember that cosine square x equals cosine 2x plus 1 over 2. Hence, for this case, cosine square 2x, we can convert it into cosine 4x plus 1 over 2. So it becomes integration of 4 integration from 0 to pi over 8 cosine 4x plus 1 over 2 dx. We simplify, we get 2 integration from 0 to pi over 8 cosine 4x plus 1. Then we can perform the integration. Integration of cosine 4x, we get sine 4x over 4. Integration of 1, we get x. The rest, we copy the 2 here, right, times sine 4x over 4 plus x, limit from 0 to pi over 8. And now we can substitute the x equals to pi over 8. We get sine 4 times pi over 8 over 4 plus pi over 8. And then we substitute x was 0. So look at here, right? Sine 0, we get 0. X is 0 as well. So we just minus 0 here. Then we can calculate the values, which gives us 2 times 1 over 4 plus pi over 8. And the answer is 1.29, rounded off to 3 significant figures. For B, integration from 5 to 10, 2 sine 3x minus 5 plus 3 cosine 2x plus 3 dx. So we can integrate them one by one. So if we integrate 2 sine 3x minus 5, we get negative cosine 3x minus 5 over 3. Integrate 3 cosine 2x plus 3, we get 3 sine 2x plus 3 over 2. Okay, and the limit from 5 to 10. Simplify, we get negative 2 over 3 cosine 3x minus 5 plus 3 over 2 sine 2x plus 3, limit from 5 to 10. Then we substitute x to 10 and x to 5 inside the expression with a minus. And now we can calculate the values, which is negative 1.9301 minus 1.1896. And we get the answer, negative 3.12, which is rounded off to 3 significant figures. Now, let's learn how to apply properties of integrals. Here's an example. Given that integration from 1 to 5 fx dx equals 6, evaluate each of the following. A. Integration from 1 to 5 6 fx dx. B. Integration from 5 to 1 fx minus x squared over 2 dx. And C. Integration from 1 to 3 fx minus 2 dx plus integration from 3 to 5 fx plus x dx. Here is the solution. For A, integration from 1 to 5 6 fx dx, we can take out the 6 so that it won't affect the integration. So it becomes 6 integration from 1 to 5 fx dx, which is 6 times 6 equals 36. For B, integration from 5 to 1 fx minus x squared over 2 dx, we can integrate them separately, which is integration from 5 to 1 fx dx minus integration from 5 to 1 x squared over 2 dx. And notice that the limit has changed. Instead of 1 to 5, it is 5 to 1. So which means integration from 5 to 1 fx dx is negative 6. And for the second integration, so we can take out the constant, which is minus half integration from 5 to 1 x squared dx. So when we integrate x squared, we get x cubed over 3, and the limit is from 5 to 1. So substitute the values, x equal to 1, which is 1 over 3, minus substitute x equal to 5, which is 5 cubed over 3. So we calculate the values, it is 44 over 3. Now for C, integration from 1 to 3 fx minus 2 dx plus integration from 3 to 5 fx plus x dx. So we can integrate them separately, which gives us integration from 1 to 3 fx dx minus integration from 1 to 3 to dx plus integration from 3 to 5 fx dx plus integration from 3 to 5 x plus x dx. Now we can combine. We can see that integration from 1 to 3 fx dx and integration of 3 to 5 fx dx, which becomes integration from 1 to 5 fx dx. So minus the remaining, we just copy integration from 1 to 3 to dx, we copy down. Integration from 3 to 5 x dx, we just copy down. Okay, so we know that integration from 1 to 5 fx dx is 6, and we integrate 2, we get 2 times x limit from 1 to 3. Integration of x, we get x squared over 2, limit from 3 to 5. Then just substitute the value, calculate with calculator, and we get the answer is 10. Okay, now you can try this example yourself. Given that integration from 1 to 3 fx dx equals 5. A. Evaluate integration from 3 to 1 fx minus 3 dx. B. Find the value of m for which integration from 1 to 3 m over x squared plus fx dx equals 0. C. Find the value of k for which fx equals 3x squared plus k. Okay, you can pause the video and try to solve it yourself. Here is the solution for A. Given that integration from 3 to 1 fx minus 3 dx, so we can split this into integrate them differently. So integration from 3 to 1 fx dx minus integration from 3 to 1 3 dx. So the limit has swapped. So integration of 3 to 1 fx dx will be equals to negative 5. Then we integrate 3x. We integrate 3, we get 3x, and limit is 3 to 1. Okay, so substitute x equal to 1 minus substitute x equal to 3, and when we calculate, the answer will be 1. For B, integration from 1 to 3 m over x squared plus fx dx equals to 0. So we can say that integration from 1 to 3 m over x squared dx equals negative integration from 1 to 3 fx dx. And we know that integration 1 to 3 fx dx is negative 5. M is a constant, so we can factorize the m outside the integration. So it becomes m integration from 1 to 3 x to the power of negative 2 dx equals negative 5. When we integrate x to the power of negative 2, we get x to the power of negative 1 over negative 1, limit from 1 to 3. So we substitute x equals to, we simplify first, take out the negative 1, which becomes negative m. And now we substitute x equals to 3, which is 1 over 3, minus substitute x equals to 1, which is minus 1 here. Okay, equals to negative 5. We solve this equation, we get m equals to negative 15 over 2. For C, it is given that integration from 1 to 3 fx dx equals to 5, and fx is 3x squared plus k, so we just substitute fx into the integration. We get integration from 1 to 3, 3x squared plus k dx equals to 5. Right, then we can start to integrate. Integration of 3x squared, we get x cubed. Integrate k, we get kx. Limit from 1 to 3 equals to 5. Then substitute x equals to 3, we get 3 cubed plus 3k. Then minus substitutes x equals to 1, which gives us 1 plus k equals to 5. Right, then we solve this equation, which we get 26 plus 2k equals to 5. K is negative 21 over 2. This is the answer for C. Remember differentiation and integration techniques that we have learned in indefinite integrals. This applies to definite integrals as well. Now, let's look at this example. Show that d over dx, x squared over 1 minus 5x equals 2x minus 5x squared over 1 minus 5x squared. Hence, evaluate integration of 0 to 1, 6x minus 15x squared over 1 minus 5x squared dx. Here is the solution. The steps are very similar with differentiation and integration in indefinite integrals. So firstly, we have to differentiate x squared over 1 minus 5x in terms of x. So from here, we can apply quotient rule, which gives us 1 minus 5x times 2x minus x squared times negative 5 over 1 minus 5x squared. We expand the bracket, which we get 2x minus 10x squared plus 5x squared over 1 minus 5x squared. Simplify, we get 2x minus 5x squared over 1 minus 5x squared. And it is same as the answer given in the question, hence shown. Next, we want to integrate the expression given. So we should start from this, which is 2x minus 5x squared over 1 minus 5x squared equals d over dx x squared over 1 minus 5x. Now I integrate from 0 to 1, 2x minus 5x squared over 1 minus 5x squared dx equals x squared over 1 minus 5x from 0 to 1. And do notice that this integration is not the same as the one given. So what I need to do is I have to multiply a 3 here, which multiply 3 both sides, I will get also 3 times x squared over 1 minus 5x from 0 to 1. Because when I multiply these 3 inside, let's see what will happen. It becomes integration from 0 to 1, 6x minus 15x squared over 1 minus 5x squared dx, which is the same as the integration that we want to find the answer. Okay, so then from here, just substitute x equals to 1 minus x equal to 0. So this is what we get. Hence, the answer is negative 3 over 4. Okay, now you can try this example yourself. Show that d over dx sine x over 1 plus cosine x can be written as k over 1 plus cosine x and state the value of k. Hence, evaluate integration from 0 to pi over 6 sub 3 over 1 plus cosine x dx. You can pause the video and try to solve it yourself. Here is the solution. First, we want to differentiate sine x over 1 plus cosine x. So we can apply product rule, which gives us 1 plus cosine x times cosine x minus sine x times negative sine x over 1 plus cosine x squared. Then we expand the bracket, we get cosine x plus cosine square x plus sine square x over 1 plus cosine x squared. Okay, and notice that cosine square x plus sine square x equals to 1. Hence, it becomes cosine x plus 1 over 1 plus cosine x squared. So, we can cancel cosine x plus 1 and 1 plus cosine x squared, which becomes 1 over 1 plus cosine x. And we compare the expression given, we can say that k equals to 1. Okay, now the next one, we want to integrate this expression. So we start from the differentiation result we get, which is 1 over 1 plus cosine x equals d over dx sine x over 1 plus cosine x. So then we can multiply sub 3 over 1 plus cosine x equals sub 3 d over dx sine x over 1 plus cosine x. Then followed by, we integrate 0 to pi over 6 sub 3 over 1 plus cosine x dx equals sub 3 sine x over 1 plus cosine x from 0 to pi over 6. and substitute x equals to pi over 6, we get sine pi over 6 over 1 plus cosine pi over 6 minus replace x equal to 0. So sine 0, we get 0, so we just say minus 0. Okay, and the answer will be 0.464. The answer has been rounded off to 3 significant figures. Now, let's see how we can differentiate the integrate with multiple functions. Here is the example. A. Differentiate x minus 1 times e to the power of negative x with respect to x. B. Hence find integration from 0 to 1 x times e power negative x dx. Leave your answer in exact form. So here is the solution. First, we differentiate x minus 1 times e to the power negative x with respect to x. So we can use product rule, which we get e to the power negative x times 1 plus x minus 1 times e to the power negative x times negative 1. And we get e to the power negative x minus x, e to the power negative x plus e to the power negative x, which the answer is 2 e to the power negative x minus x times e to the power of negative x. You can factorize the e to the power negative x, then bracket 2 times x, 2 minus x. So from here, we can put it into the fraction, which is 2 minus x over e to the power of x. Now, we want to integrate x times e to the power negative x. We can start from 2e to the power negative x minus xe to the power negative x, which is from here. So it is equal d over dx x minus 1 e to the power negative x. So if I integrate from 0 to 1 2e to the power negative x minus xe to the power negative x dx, it is equals x minus 1 e to the power negative x from 0 to 1. Then we can integrate this expression separately, which is integrate from 0 to 1 2 times e to the power negative x dx minus integration from 0 to 1 x e to the power negative x dx. So equals x minus 1 e to the power negative x from 0 to 1. So we make integration from 0 to 1 x e to the power negative x dx the subject. Hence we get integration from 0 to 1 2e to the power negative x dx minus x minus 1 e to the power negative x from 0 to 1. And we integrate 2e to the power negative x. It becomes 2 times negative e to the power negative x from 0 to 1. And we can solve this part, which we get 0 minus 0 minus 1 e to the power negative 0. And we get negative 2 times 1 over e minus 1 minus 1, which is 1 minus 2 over e. Let's try this example yourself. A. Differentiate 1 over 2 x cosine 2x with respect to x. B. Hence shows that integration from 0 to pi over 2x sine 2x dx equals to pi over 4. You can pause the video and try to solve it yourself. Here is the solution. For A, we can differentiate d over dx half x cosine 2x. Then we apply the product rule, which is we take out the half and then x times negative sine 2x times 2x plus cosine 2x times 1. Then we simplify, we get half bracket cosine 2x minus 2x sine 2x, which is half cosine 2x minus x sine 2x. For B, we want to integrate x sine 2x. We should start from the result of the differentiation in A, which is half cosine 2x minus x sine x equals d over dx half x cosine 2x. So if integrate from 0 to pi over 2, half cosine 2x minus x sine 2x dx, we get half x cosine 2x from 0 to pi over 2. Notice that we want this expression x sine 2x, so we want this part. Therefore, we integrate these two functions differently, which is integration from 0 to pi over 2 half cosine 2x dx minus integration from 0 pi over 2 x sine 2x dx equals half x cosine 2x from 0 to pi over 2. Then we make integration from 0 pi over 2 x sine 2x dx the subject. Alright, so which equals integration from 0 pi over 2 half cosine 2x dx minus half x cosine 2x from 0 to pi over 2. So we can integrate half cosine 2x dx, we get sine 2x over 4 from 0 to pi over 2. Okay, we time it half here because of this. Right, then minus, we can solve this part, right? Substitute x to the pi over 2, we get pi over 2 cosine pi. Okay, and then from here, sine 2x, if we substitute x equals to pi over 2, we get 0. If we substitute x equal to 0, we also get 0. Hence, this whole function, we get a 0. For cosine pi, we get negative 1. So, the answer will be pi over 4. We have known that integration is all about the area under a curve. So now, let's talk more in details about the area under a curve. Basically, there are three types of the area under a curve that we will discuss here. Type number 1, the area under the curve bounded by the x-axis. So, there are two types under type 1, which is the first one is the region above the x-axis. Here is how it looks like. Let's say I have the x and y axis, and this is the curve with the equation y equals to fx. And this is our lower limit, which is a. This is our upper limit, which is b. Hence, we want to find the area of this region. So this region is above the x-axis and it is under the curve. So, to find the area of the shaded region, it will be a equals integration from a to b fx dx. The second type of the area under graph bounded by the x-axis is the region below the x-axis. So how does it look like? Here it is. We have the x and the y-axis, and this is our curve with the equation y equals fx. So this is our lower limit, which is a, and this is our upper limit, which is b. So if it is under the x-axis, if we integrate from a to b fx dx, we get a negative value. Therefore, to find the area of this shaded region, which is bounded by the x-axis and the curve, so the area of the shaded region will be a equals modulus integration from a to b fx dx, because we will get a negative value, but for the area, it should be always positive. Number 3, region above and below the x-axis. Sometimes it involves both sides, above and below. So this is one of the example how it looks like. For example, I have a curve with the equation y equals fx. And this is my lower limit a, this is my upper limit b, and another limit c. So, to find the area of this shaded region, it will be area of the shaded region will be a equals integration from a to b fx dx plus modulus integration of b to c fx dx, because we know that when we integrate this region, we will get a negative value. So we always take the positive value of the integration. Type number 2, bounded by the y-axis. It is similar with the area under the curve bounded by the x-axis. There are three smaller types. The first one is the region on the right side of the y-axis, and this is how it looks like. I have the x-axis and the y-axis, and this is the curve with the equation x equals fy. So this is my lower limit, which is a. This is my upper limit, which is b. I want to find the area of this shaded region. So the area of the shaded region will be a equals integration from a to b fy dy. Notice that how I write the integration. Now we integrate function fy in terms of dy. So number 2, region on the left side of the y-axis. This is how it looks like. I have the x and the y-axis, and this is a curve with x equals fy. This is my lower limit, which is a. This is my upper limit, which is b. So we know that if we integrate from a to b, fy dy, we will get a negative value because it is at the left side of the y-axis. Hence, to find the area of this shaded region, it will be a equals modulus integration from a to b fy dy. Number 3, region on the left and the right side of the y-axis. So it is the combination of type 1 and type 2, which is, this is an example how it looks like. So this is a curve with the equation x equals fy. So I have a lower limit a, the middle limit b, and the upper limit c. So to find the area of this shaded region will be a equals modulus integration from a to b fy dy plus integration of b to c fy dy, because we know that this region will get, when you integrate, we get a negative value, so we have to put modulus sign. So in other words, when you look at the graph and find the region, you have to be aware which region will give you a negative value. Then you have to put a modulus sign. Type number 3 for the area under a curve is the region bounded by a curve and a line. So basically, it is a combination of the area of a curve and the area under a line. To illustrate the condition, let's look at this graph with the x and the y-axis, and this is a curve with the equation y equals fx. This is the lower limit a, and this is the upper limit b. To find the area of this region, like what we have learned in type 1, so the area a1 equals integration from a to b fx dx. Then we have a second graph with a straight line, and the equation of this straight line is y equals gx. So this is the lower limit a, and this is the upper limit b. This is the shaded region, and I want to find the area of this shaded region, which is a2, will give us integration from a to b gx dx. Now, if I combine these two graphs together, this is how it looks like. This is the curve with equation y equals to fx. This is a straight line with the equation of y equals to gx. This is the lower limit a, and this is the upper limit b. I want to find the area of this shaded region. So, the area of this shaded region will be a equals a1 minus a2, which is integration from a to b fx dx minus integration from a to b gx dx. Now, let's look at this example. Given this diagram with this curve, and the equation is y equals 3x cubed. This is the lower limit 3, and this is the upper limit 5. This is the shaded region. The question is, the figure shows part of a curve y equals 3x cubed. find the area of the shaded region. So here's the solution. To get the area, we need to integrate from 3 to 5 3x cubed dx. So if we integrate it, we get 3x to the power 4 over 4 from 3 to 5. We can factorize the constant, which equals 3 over 4 times 4 x to the power 4 from 5 to 3. And we substitute x to the 5 and x to the 3. We get 5 to the power 4 minus 3 to the power 4 times 3 over 4. And the answer is 408 units squared. Now, let's try this example yourself. 1. Express 6 plus 4 tangent square x over 3 as a plus b secant square x over 3. 2. The diagram shows part of the curve y equals 6 plus 4 tangent square x over 3. So here is the diagram. Use the result in part 1. Find the exact area of the shaded region enclosed by the curve, the x-axis and the lines x equals pi over 2 and x equals pi. You can pause the video and try to solve it yourself. Here is the solution. For 1, notice that we want to change the tangent square into secant square. Therefore, we can use the identity, which is 1 plus tangent square a equals secant square a. This identity connects the tangent square a and the secant square a. So, from the given expression 6 plus 4 tangent square x over 3, it is equals 6 plus 4 bracket secant square x over 3 minus 1. Then we expand the bracket, we get 6 plus 4 secant square x over 3 minus 4. Simplify, we get 2 plus 4 secant square x over 3. So, we have expressed this expression into this form. Solution for part 2. To find the area of the shaded region, so we need to integrate from pi over 2 to pi. So 6 plus 4 tangent square x over 3 dx. Then we can change 6 plus 4 tangent square x over 2 to be 2 plus 4 secant square x over 3. So the area becomes integration from pi over 2 to pi 2 plus 4 secant square x over 3 dx. And now we can start to integrate. Integrate 2, we get 2x. Integrate 4 secant square x over 3, we get 4 tangent x over 3 over 1 over 3. And the range from pi over 2 to pi. Then we simplify, we get 2x plus 12 tangent x over 3 from pi over 2 to pi. Now we substitute x equals to pi into this expression and x equals to pi over 2 into this expression. In between is a minus. Then we start to calculate, which we get pi plus 12 sub 3 minus 12 sub 3 over 3. Notice that we don't use calculator value. We use the exact value because the question asks us to find the exact area of the shaded region. So tangent pi over 3 is sub 3. Tangent pi over 6 equals sub 3 over 3. So we simplify, we get pi plus 12 sub 3 minus 4 sub 3, or it is pi plus 8 sub 3 units squared. Now let's see example about area above and below the x-axis. Here is the example. The figure shows part of the curve y equals x minus 1, x minus 2. So here is the figure. Find the total area enclosed by the curve y equals x minus 1, x minus 2 and the x-axis, which is the shaded region. So here's the solution. From the equation given, y equals x minus 1, x minus 2, we can expand, we get y equals x squared minus 3x plus 2. From here, we can label this region as A1 and this region as A2. So the total area of the shaded region will be equals A1 plus A2. Now we can find the area of A1 and A2 separately. So A1 will be integration from 0 to 1 x squared minus 3x plus 2 dx, and A2 will be integration from 1 to 2 x2 minus 3x plus 2 dx. So why do we want to separate these two regions? Remember that if the region is below the x-axis, when we integrate, we will get a negative value. So that's why we have to put the modular sign here. And now we can integrate them separately. So x squared, we get x cubed over 3, minus 3x, we get minus 3x squared over 2, 2, we get 2x. So repeat the same process for this expression. We get the same result for the integration, but the range for the first integration is from 0 to 1, and for the second integration is from 1 to 2. Then we substitute x to 1 and x to 0 for the first expression, we get this result. For the second expression, then we will get these results. After that, we can calculate the values. We get 5 over 6 plus modulus 2 over 3 minus 5 over 6, and the answer is 1 units square. Now you can try this example yourself. The figure shows part of a curve y equals 2x cubed. Here is the figure. Find the area of the shaded region. You can pause the video and try to solve it yourself. Here is the solution. So first we label this region as A1 and this region as A2. So the total area of the shaded region will be A1 plus A2. Notice that A1 is below the x-axis, so we should expect we get a negative value. Therefore, it will be a modulus function here. So for A1, it is modulus integration from negative 2 to 0, 2x cubed dx. For A2, it's just integration from 0 to 3, 2x cubed dx. So this is another way we can do if you don't like to manage modulus sign here, by switching negative 2 and 0 to integration from 0 to negative 2. So we get integration from 0 to negative 2, 2x cubed dx, plus integration from 0 to 3, 2x cubed dx, because recall that integration from a to b fx dx, if we swap a and b the position, we will get negative integration from b to a fx dx. So by doing so, a1 will become positive. Now we can integrate separately. So 2x cubed, we get x power 4 over 2. Similarly, 2x cubed for second integration is also x power 4 over 2, but the range is different. For the first integration is from 0 to negative 2. For the second integration is from 0 to 3. Now substitute the values, we get half negative 2 to the power 4 minus 0 plus half 3 to the power 4 minus 0. We calculate and we get the answer is 97 over 2 units square. Now let's see how to find the area bounded by a curve, the y-axis, and a line. Here's an example. The figure shows part of a curve x equals y minus 4 squared. So here is the figure. Find the area of the shaded region. Okay, here is the solution. It is given the coordinates of this point is -1 and 3. Therefore, the lower limit for this point will be 3. And given the coordinates of this point is 1 and 5, so the upper limit for this point is 5. Then I label this region, the white region, as A1, and this white region is A2. So the total area for this A1 plus A2 will be integration from 3 to 5 y minus 4 square dy. So when we integrate, we get y minus 4 cubed over 3, the range from 3 to 5. Then we substitute 5 and substitute 3 inside, we get 1 over 3 minus -1 over 3, which gives us 2 over 3 units square. But this is not the region that we want to find. So we want to find the area of the shaded region. So it will be the area of the rectangle. So can you see the rectangle, which is this whole rectangle? Okay, and then minus A1 plus A2. So this rectangle will be, the width is 1. So this is 1 units. And the height is 2 units. So the area of this rectangle will be 1 times 2. So minus 2 over 3, which is A1 plus A2. And the answer for the shaded region will be 4 over 3 units square. Now, you can try this example yourself. The figure shows part of a curve y equals ln x. Here is the figure. Find the area of the shaded region. You can pause the video and try to solve it yourself. Okay, here's the solution. Maybe when you want to try to solve this question, you might face a problem, especially when you are trying to find the area of this shaded region by assuming that this region is bounded below the curve and the x-axis. The problem that you will face is because we don't know how to integrate ln x. So that's why we shouldn't look at the area which is bounded by the curve and the x-axis. Instead, we should look at the curve, the area bounded by the curve and the y-axis. Therefore, we draw a straight line here, and this value and this region we call it A1. So when x equals to 4, y is ln 4. Therefore, this is ln 4. So given that y equals to ln x, we have to make x the subject, which is equal e to the power y. So A1 equals integration from 0 to ln 4 e to the power y dy. After integration, we get e to the power y from 0 to ln 4. So substitute y equals ln 4, we get e to the power ln 4 minus x go to 0, so e to the power 0. Then we get 4 minus 1, and it is 3 units squared. So to get the area of the shaded region, it is the area of the rectangle minus A1. So do you see the rectangle? This is the rectangle. Okay, and then minus the A1, we get the area of the shaded region. So now, the width of this rectangle is 4, and the height of this rectangle is ln 4. Therefore, the area is 4 ln 4. Then minus 3, which comes from A1. Then the answer will be 2.55 units square. Do you get the answer correctly? Next, how about finding the area bounded by a curve and a line? So here is the example. Given this diagram, and the question is, the figure shows the line y equals 7 minus 1.5 x, intersecting the curve y equals x squared at P, and the y-axis at Q. Find 1. The coordinates of P and Q. 2. the area of the shaded region. Here's the solution. To find the coordinates of the P, we just need to solve simultaneous equation for the line and the curve. So the equation of the curve is y equals x squared. The equation of the straight line is y equals 7 minus 1.5 x. So by equating them together, x squared equals to 7 minus 1.5 x. So both sides I multiply by 2, I get 2x squared equals 14 minus 3x. So bring all the terms to the left hand side, we get 2x squared plus 3x minus 14 equals 0. Factorize, we get x minus 2 times 2x plus 7 equal to 0. Therefore, x equals to 2 or x equals to negative 7 over 2. And since P is at the right hand side of the y-axis, therefore the x should be positive and x equals to negative 7 over 2 is rejected. Now the y is equals 2 squared, which is 4, which means the coordinates of P is 2, 4. To get the coordinates of Q, since Q is at the y-axis, hence the x-coordinate of the Q is 0, so we substitute x to 0 into the equation of the straight line, which is y equals 7 minus 1.5 times 0, and y is 7. Therefore, the coordinates of Q is 0, 7. Now number 2, to find the area of the shaded region. So first, we can draw a straight line here, and we take P as the reference, which is coordinates is 2 and 4. The coordinates of Q is 0 and 7, which means this line, this point will be 4, and this point will be 7, and this point will be 2. So we label this region as A1, which is a right angle triangle, and this region as A2, which is the area bounded by the curve and the y-axis. So given that y equals to x squared, we make x the subject, so x equals to y to the power of half. Therefore, the area of the shaded region will be equals A1 plus A2, where A1 is the right angle triangle, which is half times 2 times the height, which is 7 minus 4. And then to find A2 is the integration bounded by the y-axis, so integration from 0 to 4, y to the power of half dy. So the area of the A1 will be 3, because 2 and 2 cancelled, so 7 minus 4 is 3. Now to find the A2, just integrate y to the power of half, we get y to the power of 3 over 2 over 3 over 2, the range from 0 to 4. So substitute or take out the 3 over 2 becomes 2 over 3, so it's 3 plus 2 over 3 times 4 to the power of 3 over 2, and the answer is 25 over 3 units square. There's another method. Maybe you can see the area under the graph and above the x-axis. So the area of the shaded region will be area of the trapezium minus A3. So do you see the trapezium, which is this shape from here to here and here? So this is the trapezium. So it will be half times 4 plus 7 times 2, which is the area of the trapezium, and then minus integration to get the A3 is integration from 0 to 2 x squared dx. So the area of the trapezium is 11, and area of A3 integrate x squared, we get x cubed over 3 from 0 to 2, so we get 11 minus 8 over 3, and the answer is the same, which is 25 over 3 units square. Alright, now you can try this example yourself. Given this diagram, so the diagram shows part of the curve y equals 2x plus 1 over x minus 1. Points P with the coordinates 2 and 5 and Q with the coordinates 4 and 3 lies on the curve. By expressing 2x plus 1 over x minus 1 in the form a plus b over x minus 1, where a and b are constants, find, showing full working, the area of the shaded region. You can pause the video and try to solve it yourself. Here is the solution. So from this diagram, given that 2x plus 1 over x minus 1 is an improper fraction, I hope that you still remember how to determine if this fraction is improper fraction or proper fraction. So since this is improper fraction, we need to perform long division. So this is long division. 2x plus 1 divided by x minus 1. So x minus 1 times 2, we get 2x minus 2. So 2x minus 1 minus 2x minus 2, we get 3. Hence, 2x plus 1 over x minus 1 can be rewritten as 2 plus 3 over x minus 1, where a is 2 and b is 3. Okay, so now we can draw a straight line here, which is 2, and this line is 4. This point is 5, and this is 3. Okay, so now I want to find the area of the shaded region. Most likely, I want to find the area of the trapezium minus A1. So we label this as A1. So it's the area of the trapezium minus A1. Where is the trapezium? So this is the trapezium. Okay, so the area of trapezium will be half times 3 plus 5. Okay, then times 4 minus 2. Then we get a minus. To get A1 is integration from 2 to 4, 2x plus 1 over x minus 1 dx. So the area of the trapezium will be 8. And we can't just integrate directly 2x plus 1 over x minus 1. So we have to change to the proper fraction, which is 2 plus 3 over x minus 1 dx. Alright, then we can integrate 2, we get 2x. Integrate 3 over x minus 1, we get 3 ln x minus 1. Okay, so it becomes 8 minus 2x plus 3 ln x minus 1 from 2 to 4. Substitute the values, we get 8 minus 2 times 4 plus 3 ln 4 minus 1 minus 2 times 2 plus 3 ln 2 minus 1. And we calculate everything, we get the answer is 0.704 units squared. Now, let's look at more examples on area bounded by a curve and a line. Here is another example. Given this diagram, the diagram shows part of the curve 2x squared equals y minus 3. The tangent to the curve at point A, negative 2, 11, intersects the y-axis at B. Find, number 1, the equation of tangent AB, 2, the coordinates of B, and 3, the area of the shaded region, ABC. Here is the solution. To find the equation of the tangent ABC, we need to do differentiation. So, given the equation 2x squared equals y minus 3, we make y the subject. So, y equals 2x squared plus 3, hence dy dx equals 4x. Then, we take the x coordinate of point A as the x value. So when x equals negative 2, dy dx equals 4 times negative 2, which is negative 8. So this is the gradient of the tangent line. Then we can form the equation of the line AB. by using the coordinates of A, where the x value is -2, the y value will be 11. So applying this equation, this formula, y minus y1 equals m, x minus x1. So y minus 11 equals -8, x plus 2. Then we expand the bracket, y minus 11 equals -8x minus 16, and make y the subject, so y equals -8x minus 5. This is the equation of the line AB. Number 2, to find the coordinates of B, we know that B is the y-intercept. Therefore, the x is 0. So we just let x to 0 from the equation of the line AB. So y equals -8 times 0 minus 5. The answer is -5. So the coordinates of B is 0, -5. Here is solution for 3. You might tend to try to find the area of the shaded region bounded by the y-axis. But here's the problem. You want to find the area by assuming that it is bounded by the y-axis. You have to make x a subject, and the equation become complicated. It is still possible to find the area of the shaded region using this approach, but the process will be more complicated. Therefore, I will prefer to find the area of the shaded region by assuming that it is bounded to the x-axis. So first, I draw this straight line, and this is -2. The coordinates of B is 0, -5. I label this triangle, the area of this triangle, as A1, and the area of this triangle is A2. So the equation of the line is y equals -8x minus 5. So when y equals 0, x is -5/8. So this is A1 will be half times -2 plus 5/8 times 11. So which means that I'm finding this length. So the -5/8 is at this point. -5/8. Okay, the height is 11, so A1, the answer is half times 2 minus 5/8 times 11. We get 121/16 units squared. Okay, to find the area of A2, which is half times the base is 5/8, the height is 5, and we get A2 is 25/16 units squared. So now, to find the area of the shaded region, it is equals integration from -2 to 0, 2x squared plus 3 dx minus A1 plus A2. Okay, so integration of 2x squared, we get 2x cubed over 3. Integration of 3, we get 3x. So it is from -2 to 0, and minus 121/16 plus 25/16. So substitute the values, we get 2 times 8/3 plus 3 times 2 minus 96/16, and the answer is 16/3 units squared. Alright, now it's your turn to try this example yourself. Given this diagram, the diagram shows the graph of the curve y equals 1/6 times e to the power 4x plus 2. The curve meets the y-axis at the point A. The normal to the curve at A meets the x-axis at the point B. Find the area of the shaded region. You can pause the video and try to solve it yourself. So here is the solution. Given the equation y equals 1/6 times e to the power 4x plus 2. So now the question is, you want to find the area, you want it to be bounded to the x-axis or bounded to the y-axis. For me, I will choose it to be bounded to the x-axis because the process will be much easier, given that the equation is y equals 1/6 times e to the power 4x plus 2. If you want to make it to bounded by the y-axis, we need to make x the subject for this equation, but the process will be very complicated. So we differentiate dy over dx equals 4 over 6 times e to the power 4x. Then it is 2 over 3 e to the power 4x. When x is 0, we get y equals 1 over 6 e to the power 0 plus 2, where y equals to half, which means the coordinates of a is 0, half. Okay, so we are trying to find the equation of the normal. Now, when you substitute x equals 0, dy over dx is 2 over 3 e to the power 4 times 0, we get 2 over 3. So this is the gradient of the tangent. And to find the gradient of the normal, it will be negative 1 over the gradient of the tangent, which gives us negative 3 over 2. So we can find the equation of the normal, which is y minus y1 equals m normal times x minus x1. So y minus half equals negative 3 over 2 times x minus 0. So these values is the coordinates of a, and this is the gradient of the normal. There I make y the subject, so y equals negative 3 over 2x plus half. So when y equals to 0, we substitute into this equation, 0 equals negative 3 over 2x plus half, we get x equals 1 over 3. So this is the coordinates of b, where b is 1 over 3, 0. So I label here 1 over 3. Next, to find the area of the shaded region, so it will be integration 0 to 1 over 3, 1 over 6 e to the power 4x plus 2 dx. So which is the area under the graph from this to this. Okay, and then minus the area of this right angle triangle, which is half times the base is half, the height is 1/3. Okay, and then just integrate e to the power 4x, we get e to the power 4x over 4. Integrate 2, we get 2x. So the rest you just copy 1 over 6, and the range is from 0 to 1/3. So half times 1 over 3, we get negative 1 over 12. Okay, substitute the values, we get 1 over 6 bracket e to the power 4, 1 over 3 over 4 plus 2 times 1 over 3 minus e power 0 over 4 minus 1 over 12. Right? And you just press calculator. The answer will be 0.144 units square. Alright, that's all for this video. Thanks for watching. Do you have any questions or thoughts to share? Feel free to write it down in the comment. I would love to hear from you. Do you like this video? Please don't forget to like it and share it with your friends. Until then, I will see you in the next video. Have a great day ahead.